I'm ready to talk about Bayesian reasoning for beginners. I'm going through a lecture which I can send to you by email, or you can look it up in Dropbox. I'm very happy to be here. Just to remind you, it's Wendy Olsen at the University of Manchester, Bayesian reasoning for beginners. The lecture's around an hour to an hour and a quarter long, and you can interrupt it obviously and go over it again. I hope you'll enjoy the talk. It's meant for social scientists or researchers, anyone who wants to refresh or start to know about Bayesian reasoning and really Bayesian social statistics. So here we go. We've got a lecture planned with exercises and spreadsheets and additional readings which are in my pile here. And this has three parts. We'll start with some basic terminology, so just reassuring you about what things mean and getting you started reading this literature. I have selected one textbook and one article that really help to introduce Bayesian reasoning. Then we have some binomial models and an exercise, and then continuous variables. So these models get really complicated very quickly, and that's what's so exciting about them. So I hope you'll run along with me through the whole lecture, through these three parts, and feel like you're keeping up. But if not, come back next year and you can have another bite at the apple, because it's a really tasty apple. All right, so Bayesian reasoning arises from a formula that's attributed to Bayes, and his time of writing that formula was 1763. And there were other people who discovered the same thing around the same time, and there is some, contestation around the history of this. Nevertheless, we'll call it Bayes' theorem. And I'd like to especially thank Eric Wisniewski in my department, because he helped me to learn what the great advantages were of Bayesian reasoning. And we have a master's degree and PhD where you can exercise your skills in this kind of reasoning and use them on computers with computer programming. There's also a PhD in data science, there's a master's in data science, but don't get confused because they're not the same thing. So what I'm doing today is social statistics. And there's a definition of probability using terminology which may or may not be familiar to you. So I'm going to read it out. Each time I'll be explaining what these terms are. The probability of A given B is the ratio of two other numbers. And here these are actually scalars, but they're going to blow up into functions soon. A might be an incident like, I don't know, taking a test, and B might be something else like whether the lights were working. So we have the probability of A and B in the numerator, and then on the bottom we have the probability of B. So the ratio of those two is what we call the conditional probability of A given B. So if B happens, then this is the probability of A. And Bayes' theorem kind of used the same material but reframed it in a different way. And it was so different that it was rejected by many people for many years. And I myself am 58, and it took me a long time to think that this reasoning might be very helpful. So let's read out Bayes' theorem, because here we have, instead of A, we have the data. Or some model, or it could be, you could have various things in various positions in this theorem. And actually, if you look at P of D given B and P of B given D, it might turn out this is a little bit reversible. So it's a multiple relationship between multiple things. So the probability of D given B is the probability of B given D times the probability of D. So this is a sort of background probability. And if we want, we could derive that from the thing above. Don't worry, it's not all going to be probability. We have lots of applications coming up. But this thing is really important. So I tell you what, we'll return to this later, and we'll see it in various formats. So let me tell you what I think is really important about this Bayes' theorem. Is that we could have the probability of a model on the left-hand side. So we could have B would be the data, D would be the model, and the parameters and estimates that we think are most likely on a whole range of possible values. And that turns out to depend on the probability of the data and the probability of the model itself, which we don't know. So we have unknowns in the equation. And that was quite familiar in the 1760s, but the way that this was actually done by Bayes was quite original. So here's my other slide representing Bayes' theorem, and we're going to return to this near the end of the lecture just to recap. So here I have written a theta to represent the set of parameters in a model, because in a way we can summarize a model using a list of parameters. You could have brackets A, comma, B, going up through Z. Suppose you had 26 parameters, that's all right. Then we would have the probability of the combination or the set, theta, of all those parameters. Sometimes I call it a vector, because we might stack up all the parameters in a column and think of it as alpha, beta, gamma, in reality, and then A, B, C would be the estimates of those. Or we might use the caret symbol to say A hat, B hat, C hat. Regardless of that, using Bayes' theorem, we can just rewrite this with D for data. And data is also a big block. So you could have X and Y, you could have data over time. It can include qualitative data, which is why I'm really interested in this. I'm going to apply it for mixed methods. And I'll explain that in this lecture. So here we have then the probability of the parameters given the data is a ratio of something complex in the numerator divided by the probability of the data. Now we don't actually know the probability of the data. You might say that's 1 because it's a very concrete thing. The data are given. We know the data. The unknowns is what we're concerned about. So it's almost like division by 1. But actually it's some constant. So we're going to actually use proportionality on row 2 and say that the thing on the left is actually proportional to the numerator of that and not worry very much about the probability of the data. Now if you're doing something very small scale and discrete, you might know what that numerator was, and then again it's calculable. But in many of the applications that we're going to use, it's not something you can easily calculate. Therefore, you have to be ready to actually do something with functions in each of the parts of the formula. Now on the right hand side, we've got the probability of the data given those parameters, and that's a well-known thing in statistics. That's the likelihood of a particular model theta. You might think, oh, she's going to say given the data, but the likelihood, well, the probability of the model given the data is on the left. Here we have the probability of the data given the model. So given the model means asserting that that model is a good model of the world and is a true and valid one. If that is the case, then we can work out the probability of this big XY combination block, which is labeled here D. So then we multiply by the probability of theta, which is an unknown. That's the prior. So you've heard of prior probabilities, probably, when you were looking into Bayesian reasoning. And you might think, well, what is that? Well, we may actually have some background knowledge. We could have qualitative knowledge. And we might say, well, we're going to ask some experts, or we're going to look at the past research. We're going to do a meta-analysis now. And we'll put the old values in there as P of theta. So actually, we can fill in 2 or 3 things in this complicated formula. And so for me, what's really important is to go beyond the pure deductive mathematics of it. I've presented the mathematics of Bayes' theorem, but the real question is, what does D represent and what does theta represent? It represents reality. It represents the society or the economy. So I would write it as B, the probability P of theta given reality corresponds to the probability of our estimate of theta, theta hat, you know, the set of estimates given the data. So that's assuming the data is a good representation of reality. Now it very often isn't. And you'll have to look at some of my other writings on methodology to think about why the data might not be a good representation of reality. It's very widely accepted. It might have measurement error, or it might have bad sampling. It might not even be a representative sample. But then again, some non-representative samples are very good at telling us how relationships operate, say XY relationships. So you can't be too sure, and don't give up too quickly. Now there's a way of summarizing this in words, and that's to say the probability of the estimate of theta is proportional to the likelihood times the prior. So in the end, we're moving toward knowing about all the elements of the formula, and the one on the left is the posterior probability. It's a function of theta, and it's given D, so it's kind of a function of the data. So if the data changes, then you change your function. So if you're in data science and you want to apply Bayes' theorem, then you might say, oh, I'll make a model of the Facebook statuses, and then I'll make a model of the marginal increase in the Facebook statuses. I'll take those texts of the last day, and I'll build up a model of that, and then I'll compare the 2 models. And so now I've got 2 sets of data. One is large and one is a bit smaller. But in data science, they're usually all large. And you can build up an estimate of theta by filling in some of the gaps in the formula. So it's really a clever thing, and very easy to apply, actually. So I'll be showing you some programs.